we present a novel tile-based adaptive sampling method with controllable Fourier spectra that can generate several million samples per second. Adaptive sampling distributions with good spectral properties have many important applications in graphics. For example, light integration using environment maps demands a high-quality adaptive sampling distribution. Many rendering applications also demand spectrum-specific sampling distributions. In comparison to the state-of-the-art sampling methods, tile-based methods offer the best compromise between speed and quality. However, existing tile-based methods suffer from spurious Fourier peaks and lack spectral control. Our tile-based approach overcomes these drawbacks without sacrificing speed. We introduce a novel tiling system that achieves a fast and high-quality sampling distribution with spectral control which can outperform existing state-of-the-art tile-based methods. We will first explain our tiling system, followed by the offline optimization process. Our method uses hexagons as its building blocks. From the regular hexagonal lattice, we create quasi-hexagonal regions called hex tiles, composed of lambda finer hexagons. This structure preserves the hexagonal topology of the tile lattice at finer subdivision levels. This subdivision can be recursively repeated down to any level, but further improvements are needed to achieve acceptable spectral quality. The first improvement replaces single hexagons with connected conglomerates of 3 hexagons called trihexes. These form the prototiles for our system, which contains the 11 unique geometric configurations. From each such trihex, we create a quasi-trihex using hexagonal subdivision, followed by clustering the constituent hexagons into further trihex prototiles. This process yields a decomposition for each quasi-trihex into a set of lambda trihexes. The result is a library of finite subdivision rules which can be used for hierarchical tiling. While improved, the regularity in the underlying hexagonal structure still results in an unsatisfactory spectral distribution. To disrupt this structure, we modify the border geometry of each hex tile using a stochastic process. We begin by considering triplets of connected border tiles. Each triplet of edges is characterized by 3 binary words A, B, and C, together called a triple edge modifier. A 1 bit in these words induces a local modification of the hex tile border. This stochastic process randomly selects these binary words from a set of admissible triple edge modifiers, which enforces preservation of the underlying hexagonal tiling. These irregular hex tiles can be used to fill the Euclidean plane. Each regular trihex can be transformed into several irregular trihexes using the above stochastic process. This will greatly impact the spectral quality of the underlying sampling pattern. Now we can build a finite set of subdivision rules using these irregular trihexes. As before, each irregular trihex will be subdivided into lambda subtiles, forming a library of finite subdivision rules. By applying this set of deterministic subdivision rules, we achieve our goal of creating a non-periodic hierarchical tiling. Here, tile centroids are used as sampling point bases. This centroid distribution has spectrum free of spurious peaks. To match this distribution to a user-specified target spectrum, we calculate an offset that adjusts the position of each sampling point. These offsets are computed using the following offline optimization process. We propose a method which optimizes sample locations based on the local arrangement of irregular trihexes. From each irregular trihex in our library and their possible neighbors, we generate a collection of patches characterized by unique structural indices. Each such patch contains a set of tile centroids to be optimized, after which the offset between the basis position and the optimized one is stored in a lookup table sorted by structural indices. there is one such lookup table per target spectrum optimization. Here are few results produced using our sampling system. As you can see, our method is able to generate distributions for arbitrary target spectra, including blue noise, step function, and anisotropic distributions. Interactive speed is ensured by the hierarchical nature of the tiling system and the extensive use of pre-computed lookup tables. For more results and comparisons, please refer to the paper. In summary, our contribution involves a novel hierarchical tiling system whose tile centroids form a spectrum free of spurious peaks, and a novel sampling system based on this tiling, allowing full spectral control and able to generate several million samples per second for both uniform as well as adaptive distributions. For more details, please refer to the paper. Thank you for watching this video.